M. Now the second particle, of course, we'll see exactly the same story. So the total energy of this pair due to this interaction is twice that. So the half goes away, and we have mu squared alpha over 4 pi epsilon naught all squared times r to the 6th, and then we have this complicated expression of 3 L1 dot r hat L2 dot r hat minus L1 dot L2 squared.
What is
Yes.
what is one
One half.
What is E1?
One half.
There's a different question. Stuck in
I don't understand the word it 1/2.
1/2.
discipline.
Okay.
That's
One half?
That's
Yeah. So we calculated the energy of molecule 1 due to this fluctuation, due to the presence of the second molecule. But for the second molecule, it must be the same story. When it has a fluctuation, you see the first one. So we have to add these two together, and now we have the energy of the pair. And now comes the question of, okay, but how big is this mu? So we sort of understand this, that there's an attraction basically because you make a dipole, electric field gradient pulls dipoles. So this all makes sense. So this part is good. Somehow it's orientation dependent, and we have to think about this some more. And you can sort of see how this works, that to make this as big as I can, this is negative, right? To make this as big as I can, I want these things to be, if they're this way, I want them to be parallel, right? Then I get 3 here minus 1 here, right, which is sort of 2. Whereas if they are perpendicular, then these guys are going to cancel. I get a smaller number here. We'll see the orientation dependence more clearly later, but if you meditate on this, you'll see that the energy is minimized when the rods are parallel. But first I want to think a little about how big is mu. We're talking about some quantum mechanical fluctuation. How big is it? So, well, the fluctuation is quantum mechanical, so it doesn't come from temperature. It's not because molecules are bumping into each other. It's simply due to the uncertainty principle in quantum mechanics. So, if you, again, we'll just do a dimensional argument, and the uncertainty principle can be written in 2 ways. One way is delta P, delta Q is Planck's constant, or we can write it as delta E, delta T is another Planck's constant. So the energy can fluctuate in some time interval in the same way that momentum and position are coupled. So, okay, now if we say, all right, so if we write that delta t is a time interval, and we can think of that as being the reciprocal of some frequency. Frequency is something per time, so that makes sense. So this tells us that delta E should be comparable to h nu, where nu is some frequency. And probably have already seen this expression somewhere. This is just the energy of the photon. Okay. Now, again, using dimensional analysis, we know that energy, yeah, so the question is, what is this energy? So energy has units of you can write the energy as mu times E, just on dimensional graphs. Energy of a dipole in a field is just minus mu dot E. So the units are this. And we also know that mu is alpha E, when we have some polarizability. So we can write E as mu over alpha. So we have mu squared over alpha. So this is dimensionally good. And so if we substitute this in there, then we get that mu squared is approximately equal to alpha times h nu. So this tells us, at least dimensionally, that the dipole fluctuations have to do with the uncertainty principle related to the frequency, there's some resonant frequency of the system, and the polarizability. So the more polarizable the material is, the bigger these spontaneous dipoles will be. And that makes sense. If you have a very loose system that's easy to make dipoles, it will have big dipoles in it. The polarizability is 0, you will have no dipoles. So, although this isn't very rigorous, it's a nice, at least plausibility argument, and it turns out to be correct. And so this means that now we can actually estimate this quantity, which we didn't know before. And so we have here h nu alpha squared over 4 pi epsilon naught squared times r to the 6th. So we can actually estimate the magnitude of this process, where nu is the resonant frequency of the atom. And we'll talk about this when we talk about optics, but basically you can think of an atom as a nucleus, which is a mass, and then an electron cloud, which is coupled to it as though by a spring, and we saw that when we talked about polarizability. So it's kind of like a mass spring system, and there is a resonant frequency associated with it, and that resonant frequency is in here. It turns out to be a high number, about 10 to the 15 hertz, but that's what it is. So for first principles, we can calculate the magnitude of this energy and of this van der Waals force, which holds things together. Okay, so we know this, and then the next thing to do is to think about what happens when we have a bunch of these rods together. Okay, so this is the main thing. So now we have the interaction energy, van der Waals interaction for pair of rod-like molecules. Okay, so I hope you're happy. This is a nice result. We actually understand how two polarizable molecules interact. This is really the heart of liquid crystal stuff. Right? This is the essential feature of liquid crystals. They want to be parallel because of this energy. Okay, any comments or questions on it? Everybody understands everything?
It's the interactions between two spherical molecules. The only difference should be just on the graph sphere part, right? not significantly smaller than the rod-like molecule.
Yeah, in this case, we assume there was only polarizability in one direction. But yeah, the magnitude for spherical molecules would still be this, but you wouldn't have this orientation dependent part.
So in the experiment, can we, is that, in consistence code the same as the experiment that the interaction between spherical molecules are of the same magnitude of rod-like molecules? Do we get the same result in the experiment?
Well, if the polarizability were the same, then you would get the same result. For long molecules, polarizability is higher in that direction, so you would have to somehow worry about that. But basically, yeah, this is the correct thing, and you can use this to calculate, for example, the critical temperature, right? The critical temperature where the liquid turns into a vapor from this result here, right? But this energy, if you put the separation distance to these two sort of molecular radii, then you get an energy here, and when that's equal to kT, and that's when you have the critical temperature where thermal excitations can overcome this attractive force. A better picture would have been to take molecules which are somehow sort of ellipsoids of revolution maybe, and then we would have a more complicated description of the polarizability tensor. But we would have got a result very similar to this, but a little more complicated, because then we would allow for transverse polarizability as well. But this really captures the essential features of what happens. Okay, so once again, why are we doing this? We're doing this because we want to write down the potential energy for our molecule. So, and now we know what the interaction energy is between two of them.
And nu is the resonant frequency of the rod or of the atoms in the rod?
The nu is, well, we are kind of presuming that this is just one entity, and nu is the resonant frequency of that entity associated with polarization that way.
Okay.
And again, when we do optics, we'll come back to this. You really have a complicated structure, and you can think of a complicated molecule as a bunch of harmonic oscillators. So you would have to sum over different frequencies here. Okay. The other important thing maybe that's worth noticing that, or mentioning is that, so we have oscillating dipoles in here, but it turns out that the interactions are near field interactions. I'm not sure how much that one's spending, but if you have an oscillating dipole, a dipole that's oscillating for whatever reason, then it creates an electric field, and that electric field has three terms in it. The electric field has three terms. It has a term that we have, which goes as 1 over r cubed. It has an other term which goes as 1 over r squared. It has an other term which goes as 1 over r.
And that's the near field.
And this is the near field. This is the radiation term. So, but it turns out that these molecules are so close together that this term dominates. And so it's not that there's radiation everywhere. There's energy exchange without radiation due to this very small value of R. Okay.
What corresponds to 1 over r squared in that expression? You had 1 over r cubed, 1 over r squared, so what corresponds to 1 over r squared? What corresponds?
Physically, like what does
Yes.
the 1 over r squared term mean? The r term is radiation.
The 1 over r is radiation.
Yeah, what is
The 1 over r squared term is just like 1 over r cubed, but it falls out slower.
Okay.
So yeah, it's sort of tricky. I mean, it's a really important problem is to figure out the electric field on an oscillating dipole, and you have to solve Maxwell's equations. And when you solve it, these are the terms that you get. But the point is when r gets big, you can ignore the first two terms. You get the radiation term. The energy has to go as 1 over r squared, conservation law. But in the near field, you have this 1 over r cubed, 1 over r squared, and that is responsible for energy exchange between atoms and molecules of very short lengths, and this is non-radiative energy transfer that comes up in many situations, particularly in this. Okay, now, so the picture that we have is that we have all these molecules every which way, and we want to know what the energy, so the picture that we had when we did our calculation for non-interacting rods is we just wrote down the kinetic energy for each rod, potential energy with the electric field of each rod, and then we did the partition function. And we said, oh, but all the rods essentially see the same thing, so we just ended up taking the partition function for one rod raised to the power n, because everything was the same. And we kind of want to do the same thing here. And so let us imagine now a particular rod. We're looking at this rod, and this rod will have a potential energy which will consist of its interaction with this guy, this guy, this guy, this guy, this guy, all these guys, right? So what we have to do is somehow try to figure out what this energy is, which means we have to sum. So energy of particle 1 is going to be E12 plus E13 plus E14, all of these. So we're going to have to sum over these. And that's the next thing that we're going to have to do. Now there's another point which is both important and maybe subtle, and that goes like this. If we just go back to the two-particle picture, it's got two molecules here interacting via this E12. So this energy depends on position and orientation. So if I want to know what the force is acting on this molecule here, acting on this molecule here, I have to take the derivative of this energy with respect to position. That will give me the force acting on the molecule. How much does the energy change when I move that molecule a little bit? That tells me the force acting on it. So I have to take the total energy for the pair and take its gradient to get the force. So that's good. So that means that if I want to make a potential for this particle, I should take this guy because the gradient of this gives me the force. Similarly for the torque, if I want to know the torque acting on this molecule, I should take the derivative of the pair energy with respect to the orientation of L1. I change L1 a little bit and I say how much work do I have to do to reorient it, and that will give me the torque. So to get the forces and the torques, I need to take the total pair energy and take its derivatives, and I'll get the right forces and torques. On the other hand, if I assign all of this energy to this molecule, I have to do the same for this molecule if I want to have forces and torques on it. I'm going to overcount the energy, right? I'm going to assign the pair energy to each molecule. So I need this to get the forces and torques, but giving all of it to this guy gets me into trouble. And this is kind of a universal problem in interacting systems. So what we'll do then is we'll say that the energy of particle 1 is going to be the just for these two, just for the moment, just focus on this system of only two particles. I'm going to say that the effective potential of particle 1 is going to be E12, which gives me the right forces and torques, but it overcounts the energy if I were to do this for every particle. I should really only give it half of that, right? But then I don't get the right forces and torques. So what I'll do then is I'll fix it by subtracting 1/2 of the average of this. Okay? So, whoops, 1/2. And by the average, I mean I'm going to average over the orientation and the position of particle 1, so that if I take derivatives to get forces and torques, I get nothing from here. But if I want to count the average energy, take the average of this, oh, I get the right quantity. Right? So this, I need this to get the right forces and torques. And this guy corrects for overcounting. So this is just a number. I will average over the variables, so it's just a number that prevents us from overcounting. So this is the approach that we use. And then in this way we can construct the potential energy for every particle. And then we can evaluate the partition function. We have the free energy, and we are done. So let's do it. So then in a system of lots of molecules now, the potential of one particle will be just like that, but I have to sum over all the neighbors, and I'll sum by doing an integral. So I have E12. And then to count the particles, I'm going to take the number density times d cubed r. So this is the elemental volume. So I go to a place, and then I make a little volume element times rho is the number of molecules in that little volume element, and I multiply it by the interaction energy at that point. And then I'm going to multiply this. Okay, so let's imagine doing this, right? So if I have this E1, and I'm looking at this term, I'm going to have E12 plus E13 plus E14. Okay. So I go into some region. I got a bunch of molecules here, say 2, 3, 4, 5, and I have these energies. Now, these are all more or less at the same distance from my molecule 1, so R is fixed, but the orientations are every which way. So what do? Well, I'm just going to do the same thing. I'm going to multiply by the density of orientations, if you like, and multiply by d omega. So I'm going to multiply by the orientational probability density of L hat. So this is the probability of a molecule having orientation L hat, and I'm going to integrate this over the solid angle. So I'm kind of doing the same thing with orientation that I have done here with position.
How do you call this d omega?
That's the element of solid angle.
Solid?
Yeah, element of solid angle. So this would be sine theta, d theta, d phi. And there's a shorthand for that. Okay, so is everybody happy with this? So this is basically just summing up this first term, and then we have to do this. Okay? So all we have to do is do the same thing, but average over the orientation of, I call this 2. So this means that particle 1 has a given orientation. Okay. In this energy, we have particle 1 and particle 2, so we integrate over there is the particle 2. And then when we subtract the average, we have minus 1/2, exactly the same thing, 1 to rho d cubed r, but now we average over the orientation of particle 1 as well. So it's the same as this, except we average over the orientation of particle 1, so we end up just with a number. Okay, and this gives us the potential energy of particle 1. And of course, every other rod in the system will see the same thing. So if we get this, then we can just proceed in the usual way and get the free energy. So we'll stop here, and what we'll do next time is just evaluate this integral. So remember that these guys depend both on R, we integrate that out, depend on orientation, we integrate one of those out. This guy depends on R, integrate that, and integrate both orientations. So once we do that, then we'll have a nice, simple expression for the potential energy of a particle in the system, depending on its orientation, and then we can calculate the partition function of free energy, minimize it, and we're done. Okay? Woo! Okay, I was happy to hear that. I was going to say that not all of you seem really excited about this. So it's a non-trivial calculation, but it's pretty straightforward, and it really, I think, illuminates what goes on in these liquid crystal systems. Okay, good here. Thank you. See you guys on Wednesday.